I'm Andreas Hamberger, and this is the Hamberger Report, where I cover AI governance, enterprise architecture, and the technology decisions that actually matter to the people who have to make them. If you find this useful, subscribe and hit the like button. It helps more professionals find the channel. Now let's get into it. In January 1992, a tenured professor published a message to the Usenet newsgroup comp.os.minix. The subject line was 4 words: Linux is obsolete. He was right about the theory. He was wrong about everything that mattered. I'm Andreas Hamberger. This is the Hamberger Report, where I cover the untold history of the operating system that runs the world. This is episode 3. The episode where we ask what happens when a theorist and a builder disagree about whether a technology works. One of them stakes their credibility on the architecture. The other ships the code. The theorist was Andrew Tanenbaum, a professor at Vrije Universiteit in Amsterdam. He had built Minix, a clean microkernel operating system used in universities worldwide. He had publications, credentials, the respect of the field. The builder was Linus Torvalds, a student in Helsinki. He had hacked together a monolithic kernel in his bedroom and released it to the world for free. Tanenbaum told Torvalds that Linux was architecturally obsolete. That argument began a debate that lasted years and shaped the software stack that now runs the internet. Before we get to the debate, I want to start somewhere else. I want to start with 2 colleagues of mine who recently declared that artificial intelligence was a bubble, and why I recognized the pattern immediately. Before I explain why Tanenbaum lost, I need to explain why his argument was reasonable. Linux used a monolithic kernel. The file system, device drivers, network stack, and memory management all ran together in a single privileged address space. One bad driver could crash the entire system. If you have ever experienced a kernel panic on a Linux box, you know the failure mode. The screen fills with register dumps. The machine is dead until you power cycle it. Minix used a microkernel architecture. File systems ran in user space. Drivers ran in user space. If a driver crashed, the kernel survived. The failure was contained. Tanenbaum's argument was that operating system research had moved beyond monolithic kernels. Isolation improves reliability. Modularity improves maintainability. For a system expected to run on diverse hardware across decades, these are not academic preferences. They are genuine engineering goals. He was also, in a narrow technical sense, correct that Linux sat behind the state-of-the-art. The academic consensus of 1992 favored microkernels. Tanenbaum was not arguing against consensus, he was representing it. The problem was not his analysis of the architecture. The problem was his analysis of what the architecture was competing against. He was comparing Linux to an ideal future system. Torvalds was comparing it to no system at all. Those are not the same comparison, and they do not lead to the same conclusion. Torvalds' response was blunt. He did not argue theory. He argued results. Monolithic kernels were faster. There was no message passing overhead between isolated services. System calls went directly to the kernel, not through inter-process communication layers. On the hardware of 1992, the Intel 386 and 486, this performance difference was not a benchmark footnote. It was the difference between a system you could use and one you could not. More importantly, monolithic kernels were simpler to build. A student in Helsinki could build one. A well-funded research team had spent years attempting to ship the GNU Herd microkernel and could not reach a stable release. It would take decades. The perfect architecture that cannot ship is worth less than the imperfect architecture that runs. Torvalds was not claiming that monolithic design was theoretically superior. He was claiming it worked on real hardware for real users right now. This is distinction that defines the entire history of Linux. Tanenbaum was designing for an ideal future. Torvalds was building for a messy present. The messy present won. Not because perfection does not matter, but because people needed an operating system today, not a theoretically correct one in 5 years. The community that gathered around Linux was not gathering around a theory. It was gathering around something they could install, modify and run on real hardware they actually owned. The theory was sound, the result was faster. I did not follow this debate in real time. In 1992, I did not yet know Linux existed. By 1994, when I was compiling my first kernel on a 486, the exchange was already archived on Usenet. I read it later. My opinion at the time was entirely pragmatic. I had spent 28 hours compiling that kernel and rewriting a TGA video driver to support my graphics card. Every module configured, every unnecessary option disabled. The result was a kernel tailored precisely to my hardware. Lean, fast, mine. Could I have done that with a microkernel? In theory. In practice, the tooling did not exist and the systems were not ready for the hardware I owned. Linux worked. I used it. The proof was in the compilation log. By 1997, I was Technical Services Manager at ICONZ, New Zealand's first commercial internet service provider. Some of my colleagues argued passionately for BSD. Cleaner architecture, they said, a distinguished lineage tracing back to the original AT&T Unix. They were not wrong about BSD's technical merits. But we were running production systems serving an entire country. We needed stability, speed, and a developer community large enough to resolve problems at 3 a.m. on a Sunday. Linux had the momentum, the package ecosystem, and the patch cycle. BSD could not match it. We chose Linux. The country stayed online. Pragmatism wins, not once, every time. The Tanenbaum Torvalds debate is a specific instance of a principle that Richard P. Gabriel named in 1989, worse is better. The argument, systems that prioritize simplicity of implementation over completeness of specification, spread faster, attract more contributors, and ultimately deliver more value than theoretically superior alternatives. Linux was worse than a microkernel in isolation and fault tolerance. It was better in performance and simplicity, and it had one decisive advantage: thousands of contributors who could read, modify, and improve the code without permission from anyone. The same pattern explains why Linux displaced the proprietary Unix variants that were by many technical measures superior. AIX, HPUX, and Solaris had better SMP support and better file diff reliability. They also cost thousands of dollars, ran on proprietary hardware, and were developed by small teams behind closed doors. Linux was free. It ran on commodity hardware. It was built by volunteers. Worse on paper, better in practice. But here is the part that often gets missed. Tanenbaum did not lose entirely. Loadable kernel modules allow drivers to be inserted and removed without rebooting. Android isolates applications in ways that echo microkernel principles. Docker, released in 2013, uses Linux kernel features to isolate processes in exactly the way Tanenbaum advocated. Kubernetes then orchestrated those containers at scale. Hypervisors, which underpin all cloud computing, implement hardware-level isolation that achieves what microkernels promised at the operating system level. Long, the abstraction moved up the stack rather than into the kernel. The principle survived. Good ideas from losing architectures often reappear inside winning ones. They just arrive on different terms. Those two colleagues I mentioned, the ones who declared AI a dead end. Their argument had exactly the same structure as Tanenbaum's. They identified real flaws, hallucinations, unreliable outputs, a lack of reasoning transparency. These are genuine problems. Anyone who works with large language models encounters them daily. The flaws are not imaginary, but they made Tanenbaum's error. They judged a technology by its theoretical limitations rather than its practical utility. and because they refused to use the tool, they could not see what it actually delivered. The worse is better pattern is playing out across the AI landscape right now. Open-weight models are not as polished as the best proprietary systems. Their documentation is rougher, their ecosystems younger, but they run on your own infrastructure. You can inspect the weights, fine-tune for your domain, and deploy without per token API fees. The same trade-off Linux offered in 1994, less refinement, more control. The organizations building governance frameworks around open-weight models today are making the same bet the early Linux adopters made. Control over your own infrastructure is worth more than vendor convenience. Tanenbaum staked his credibility on a theoretical objection to a tool being built by someone 23 years his junior. He was right about the theory. Torvalds was right about the result. The result won in 1992. It is winning again now. If you enjoyed this episode, subscribe. New episodes in the History of Linux series every week. And subscribe to the Hamberger Report. New videos every day. That is the Hamberger Report for today. If this was useful, subscribe and hit the like button. It helps more professionals find the channel. You will find links to everything we covered in the description below. I am Andreas Hamberger, and I will see you tomorrow.